take some other field, this is called circumferential field, right? So this is just like a circular disc inserted on a cylindrical rod. Now what is the profile area here? In the direction of its flow, you cut it x. Now this profile is looking like a rectangle. And now what is this dimension, this size? Obviously the profile area is this distance by into this distance. Right? If I can call it as height or thickness, let's say, thickness into length. Now what is the length here in this case? Radius. It's not radius, it's a difference in radius. Outer radius, if I may call it so, this is inner radius of the film. So outer radius minus inner radius. Suppose if I write this inner radius as R1 and this as R2, this will become R2 minus R1. If I take case 3, this R2 becomes R2C minus R1. That is L into this distance. So that is how you have to solve the problem. So now for this field, for circumferential field, so this is what we are discussing. LC is L plus D by 2. R2C is equal to R1 plus LC, or LC is equal to R2C minus R1. And profile area is this dimension LC into this dimension T. Right? Now you have these curves for different values of R2C by R1, which is a reflection of the size of the field, isn't it? So this outer radius by inner radius is a measure of the size of the field. Okay. So now for a particular value of this, say my R2C by R1 is, let's say 3, then I should choose this curve. And again say my value is 0.5, x-axis value. Project this here onto this curve where R2C by R1 is 3, and then project it here. Maybe 75 or no, something like that. That's how you have to solve such problems for which we don't have ready-made formula. Right? So with this knowledge now you can try to solve one problem so that you get it familiar. This is not our problem. So just a time, let me quickly explain this. So this is the physical description of the problem that you are seeing here. Please look here. And the given data is this thermal conductivity L. How did I take L here? Here it should be. Where did I get it from? Right? This is the profile. Directly the size is given as 1.5 centimeter wide and 1 mm thick. Right? So wide is with respect to reference to the view that you have. You are seeing in this direction. You can consider this as width, right? But in our convention, what is this dimension? This is in the direction of heat flow. We consider it as L, right? So 1.5 centimeter converted into meters is this L. Thickness is 1 mm. Put in meters. Fitted on a 2.5 centimeter diameter tube. Tube is the base surface, right? So that is R1 is equal to 2.5 by 2, right? And then the base temperature is 170 dB and ambient fluid temperature is 25 degrees centigrade. Heat transfer coefficient is given, and we need to find the heat transfer from the film. And now LC is equal to L plus P by 2, right? R2C is R1 plus LC, right? The outer radius. And then AM is P into LC, right? So this is the value. And the term or the value of the term combination property, let's say, on the x-axis. LC over 3 by 2 and this whole term. This substitute, this is the value that you get. And R2C by R1 is this value. And now let's see. First you locate the point, right, on x-axis which has the value of this 0.124. How do you find this? See, here it is 0, it is 0.5. The middle line represents 0.25. And if you consider these two, middle of this again should be 0.125. So roughly this is the middle point of 0, this line and this line. We should come somewhere here. Right? Like this. So now let's have this. Let's fix this. When you do it using your own data, you should have a pencil, right? And scale and roughly, very lightly mark it. Don't use pen because the same data book is to be used by some other student in the examination. Now let's look at which curve fits for our problem. R2C by R1 value is 2.2. So here we have 2, here we have 3. So in between, if you divide the area into 5 equal parts, you will get 2.2, 2.4, 2.6, 2.8 and 3. So if you assume this is divided into 5 parts and the first part is the line or curve which represents this value, right? So that being the case, there is an imaginary curve here which should go like this and then it is hitting this point, right? This is the intersection point, right? So now this point is to be projected onto the efficiency axis. So now this is 80, this is 100 and this is 90. And between 90 and 100, roughly if you see 93 or 94, when you do it, you may get it 92 or 94 or 95. That approximation you can always make because it's not possible to exactly pinpoint the curve because the distance between them is also not uniform throughout. Right? So once you find the efficiency, you know the definition of efficiency is actual heat transfer by maximum possible heat transfer. Right? And the maximum possible heat transfer, how can you find from the given fin? Maximum possible heat transfer is when the entire surface of the fin is at base temperature, fixed temperature. So then this is simply HA delta T. H into A into surface area into TB minus T. Now H into surface area into TB minus T. Now what is the surface area of circular fin? Right? Circumferential fin. It's a disc. Please imagine, right? This is the top surface and there will be bottom surface as well. Suppose if you take top surface now, you tell me what is the surface area of that. Imagine it's like a washer or disc, right? So now it's like hollow ring. What is the surface area of the top? Pi what? Come on. Huh? Pi r square. Pi r square is the area of a solid, circle. Now, this is inside radius of the fin, and this is R2C, right? Now I am asking for this area, right? This is the area that is available for heat transfer. Pi R2C square represents the total area from this point to this point of the outer circle, let's say, minus pi R1. So area of outer circle minus area of the inner circle. So therefore pi into R2C square minus R1 square. So this is one side, right, on the top side. Then same area is also available on the bottom side. So therefore you will get it if you multiply it 2 times this. So that is the surface area of the circumference. You calculate to find some and then you substitute to get this value. Please get it.